Alright, so quack like a duck. There you go. Alright, here we sit. Get at these problems. But what I wanted to do is I wanted to look at a particular problem here in which I may just do it, make up my own here. So I think I'm going to do that. I think I'm just going to make up so let's assume water from a river kind of came up and hit the wall here. Came under the wall, and let's say this is 10 feet, and say maybe it's moving 10 feet per second, all this fluid back here. So here's the water. It's coming out at a certain speed, and it's coming out at a certain depth, which I'll just call that D. What is the depth? And what is the speed? So the way we'll do this is we'll start at some location here. We'll end up at some location here. We're going to assume no losses, and then we're going to talk about that in a second. Let me make sure the stream is going okay. Give me a second. Oh, it's going okay. So what we'll do, write Bernoulli's equation between those two, between here and here, and we're going to assume no losses. Here's your losses, and I'll get you prepared for this. There's a box that we'll fill in later when we do have losses, and we'll address how you calculate those. But for right now, that's a 0, big fat 0. P2 plus gamma Z2 plus rho V2 squared over 2. We'll assume it's water, so therefore gamma is equal to 62.4 pounds per cubic foot, and the density is equal to 1.94 slugs per cubic foot. So those are those two values. I'll go ahead and erase this losses box here because I kind of need the space here. Well, let's list P, Z, and our V. Now, you can list this way, or sometimes I'll list it like this. Location 1, location 2, pressure, elevation, and V. So let's try to address some of these. Elevation, let's address that first. We're going to take the elevation from a datum, which is the bottom of the water. So in location 1, that's going to be 10 foot. So it's 10 foot up there. And the elevation over here is going to be just D. Pressure. Actually, this is atmosphere here, This is atmosphere here. So we're going to take the gauge pressure, and guess what? Now, the velocity here is 10 feet. The velocity out here is, I don't know, so I'm just going to call it V2. And I need to put a subscript over here. The depth, I'll just keep that with a D. So the question is, how do you tie? Okay, so if you look at this here, I mean, again, move some things around. Okay, so if you think about it, I know everything. I know everything at 1. I can calculate that. I know I'm missing 2 unknowns here. But I only have 1 equation. So there has to be another equation. And it turns out continuity is the other equation. So if you think about it, I didn't address this yet, but I'm going to say it's only 1 foot into the page. So this means if you're looking at the entrance, say, it's only a foot into the page, and the exit is only a foot into the page here. Okay, that being the case, now that we have that, continuity will tell you that the area at location 1 times the velocity at location 1 is equal to the area at location 2 times the velocity at the location 2. So, here, let me check the health of the stream real quick. I'm having some weird, hang on. Okay. All right, I'm back at it. So, area 1 is going to be a 10-foot tall. Let's do it this way. Area 1 is going to be, okay. Oh no, doing this. Okay. Area 1 is going to be this area. Area 2 is going to be this area. So let's head back to that. And the first entrance area is, it's 1 foot into the page, remember that. So it's going to be a 10 by 1 times the velocity running along in the front is 10 feet per second. It's 10 equals to the area 2, which is D times 1. And the velocity at the exit is velocity. So guess what? I get this. I have a choice of saying V2 is equal to 100 divided by the distance. So what I'm going to do, I haven't fulfilled these yet, so I'm going to take this area, this stuff, and move to the right here. I'll show you what I mean. I'm going to take this. This is the supporting equation. Put it over here. I'm going to go back, and I'm going to fill out this equation here, Bernoulli's equation here. In other words, this is over here. Okay, Bernoulli's equation, what does it look like? That is going to be 0, that's going to be 0. This is going to be gamma times 10, because this is location 1. Then I'm going to take my 10 and put in here, plus rho times 10 squared over 2. I'm going to take my d, put it right there, because the gamma times d. I'm going to take my v and put right here. That's rho v2 squared over 2. Now, from continuity, this is the case. So I get gamma D rho 100 over D squared over 2. So I took this whole thing, stuck it under the squared, and put it right there. Now over here I've got my 10 gamma plus rho. Go ahead and move that out to 100. Now I'm going to go ahead and start putting in the things. 10, 62.4 plus 1.94 for the density. Times 100. Another 2 is equal to 62.4 times D plus 1.94 times, see, that's 100. Okay, not slow. Okay, that's 100 squared, or that. There's a t d squared and a t there as well. So what I can do, I can multiply. Well, first, let me figure out this number. I do not know how I did that, but that's okay. Okay. So here, you'll see 1 or 10 times 62.4. So 1.94 times 100, 2, 721 equals to 62.4 D plus, and I'll figure out this number as well. However, let's do it this way. Over 2 D squared. So what I'm going to do is multiply both sides times 2 D squared. So what I get over here is, okay, so I'm going to go ahead and multiply 2 times this and this and this. So 21 times 2 times D squared equals to 2 times that, and 24.8 and 24.8 D. Now multiply this D squared and this, so that's going to give you a D, oops, already have the D, D to the third, plus, now I'm going to multiply this 2 times this, but the 2 is already here, so in fact, I just get 19400. As this, I'll cancel this, but only for that term. This 2D multiplies that, gives me this. This 2D times that gives me that. So guess what I got? I got a cubic equation. Wow. Okay. So what I'm going to do is I'm going to move things together on this. And I'm going to say I have a function of D in which, I'll go ahead and take this first one here, 124.8 D to the third minus 1442 D squared plus 19400. Now why did I put this function here? Because I want to find the roots. And the roots are where f D equals 0. If that's the case, that's the solution. So I'm just going to do something interesting here. Let's go back up and look at this thing. Okay. Now, several ways you can do it. One is you can systematically go through it. The other thing you can do is use your plotting ability inside of a MATLAB kind of octave kind of thing. So what I'm going to do is I'm going to say D equaling to, and I'm going to go ahead and include negative values, minus 100 to 100. You'll see why I'm going to shrink this down in that. And then I'm going to do f for the function equals to 124.8 times d. I have to put a period there. Minus 1442 times d. Have to do element-wise operator. And plus 19400. Okay, I should have put a, sorry about that, I should have put a semicolon at the end so it wouldn't be a mess. Plot f, oops, okay, I wanted the d to be the x component and the f. Give it a second. Plotting here is not as great as it is in MATLAB itself. Here's what you find. Okay, so first of all, going down in here, it's not a good thing. If you go up to about right here, looks like we need to be in the range of, say, maybe here and here. So, first of all, let's think about this. If we're going to the left, can you actually have a negative d? No, you can't have a negative d, so it has to start at a 0. So what I'm going to do, I'm going to go back up. I'm going to say it can't really have a negative depth. And, you know, going to 100 maybe is fully excessive. Let's plot it now. Now, we're getting something. We're getting somewhere. Okay, so in fact, there are multiple solutions here. Oh, that's right, I can't zoom in here. So, what I can do, I can zoom in like this, I think. Okay, look at this. Oh, geez. Looks to me. Oh, no. Okay. Okay, let me try to zoom again. First of all, let's zoom in on this value of 10. And if you do, zoom in closer. And then we're going to zoom in closer. And then we're going to zoom in even closer. And at this point, we've zoomed in to the point where you can't really zoom in that much more. Well, it turns out there will be the root at d is equal to 10. You see what the implications are. The implications are the water came in, came up to this gate, went under, it was a depth of 10, suddenly it came up, came back to a height of 10. In fact, there was no loss of energy, so the particle could go like this and back up to here. And in fact, what the exit speed would be 10, the entrance speed would be 10, and essentially it would be as if the water came up and was like this. There would be a little bit of water flowing fast under there, but the exit would be the same elevation as the entrance. So that's a legitimate solution. So let's take a look and see if we can back that out of the equation. And let's look at this and realize that's 10 feet. So let's back this out. So if you have this function, 124.8 d to the third minus 1442 d squared plus 19,400, and so you're going to say, I'm going to have d minus 10 b times something is going to equal to this. Well, let's see if we can get this out. Now, I'm going to rely on an old style memory that you may or may not have. And in this old style memory, if we're trying to find a root, and this is equal to 0, then d equal 10 will satisfy that. So the question is, what is this? Well, without 16 left. Oops, I copied that down. 24.8. I'm copying this down. D to the third minus 1442 d squared plus 0 times d with 19,400. Then I'm going to do something really bizarre. And I'm going to use this. So if I multiply this times d squared, and then 124.8, so I'll multiply this times that, put it down here. 24.8 d squared minus, okay, and you got a minus, and so you multiply that times 10, it would be 124.8 d squared. Okay, let me get rid of this. Sometimes they put a parentheses here. And then I subtract these two. Okay, sorry, there's supposed to be a third here because d squared times the d gives you d squared. So you get nothing here. So what do you get here? Well, you get a d squared, but you get 144.2. And then what you're doing, you're doing that. So in the interest of making things simple, 248, what is that? 198. I'm sorry, 194. Now, a plus and a plus, minus and minus gives you plus, so this still has to minus. Now what do? Well, I want to get rid of that. So 194d. So I take this times this and put it right there. D squared. And take this times this and put it right here. Okay, it's a minus, there's a minus, which is a plus. 194, but there's an extra 0 and a d. Now, I go in here and take the minus, this. Okay, so now I get minus, because this is a plus and this is a minus, which is minus 1940d. And that's because sometimes they'll copy this down. That's kind of a common thing to take this and copy down to here. These are old memories of yours that should exist. Okay, and now I'm going to copy this all the way down here. 0. Now, what do I do here? I multiply, minus 190, and that's it. So take this, and this gives me 1940d, and then I take this times that, and I put right there. It's 19400, and then what I get is nothing and nothing. So now, it goes in right here. Let's see if I can put it in right there. Is it way over? 124.8 d squared minus 194 d minus 1940, and slide that back over. Now, what I'm going to do, this mess that I've created here, I'll just go ahead, take it, slide it to the right, slide it more to the right, get it out of the way. Now, what I can do now, okay, hang on, I can use, okay, it's already found one root here, so now I'll find the roots of this. Sometimes it'll list it that way. B plus or minus the root of b squared minus 4ac over 2a. Okay, we have to identify a, b, and c. And so here's what I'm going to do. Minus, but then there's a minus in that 4, plus n or minus, and then 4 squared minus 4 times a and c, but it's a minus, and then that becomes plus 4 times 124.8, 1940, over 2 times a, which is 124.8. Then we're going to look at this on a plot. Geez, so 194 plus or minus, and I don't know what this junk is in here. Let me see. Okay. Root 194 squared plus 4 times 124.8 and then 1940. I hope I entered that all correct. 1003 divided by which I already forgot. 2 124 8 is 249.6. So I'll get a 2 roots here of, let's just go through and do this real quick. Come on. Okay. 94. I'll do a plus. I'll do the first one. Do a plus. 194 plus 1003 divided by 249.6 plus some extra digits, I'm sure. 4.79. So you get 4.79. 57? Right, 4.7956. So here's my root, 1 and 2. The next one will have a minus here. Minus 3.2, 2, and 4, 1, 2. So there's my root. So let's write this whole thing, get this equation up here, and rewrite it. I have d minus 10, d minus 4.7957, and then d plus 3.2412 is equal to 0. This is in fact that. So I get 3 roots. Okay? You get a root, a solution of either, now you have to realize this has to be 0. The only way it can be 0 is if you move the 3 to the other side, so you get a minus 3.2412, or you get 4.7957, or you get 10. This one, not even possible. You can't have a negative depth. So what do you have? You have this one being the other choice. So here's your choices. You have the choice of water coming up in the spillway, coming down like this, and it came in at 10 feet per second. There's an elevation of 10. It leaves at 4.7957, and the velocity it's leaving at is, you look back at the continuity, you have to remember it's 1 foot into the page. 1 foot into the page here as well. So the area 1, velocity 1, area 2, velocity 2, The area, nothing more than the height times 1 foot. So it becomes 10 equals to the area of the exit, 4.79 times 7. Velocity at the exit. And what you get is 100 divided by 4.79 times 7. 20, round 20.852. The other exit, and that makes sense if this was 5 and this was 10, it'd be exactly 20, but it's slightly off of the 5. So the other exit would be the 10. Water would come up, go in at 10, it would be a height of 10, and the water would just basically go up and come out. This would 10, this would be 10. Now, which one is it? I don't know. The key is, my guess is if if this thing were sitting like this, it would probably be close to this. If, however, this thing is shoved all the way down, my guess is that it would probably end up being this one. It turns out later there's a description of how this takes place. One, there's 3 things that happen here. One is Bernoulli's equation, continuity, but there's also momentum, which we haven't even gotten into yet. So these have to be satisfied. This one's absolute. This one's absolute. This one can branch off. Here's what I mean. Losses, no losses. Let's talk about what happens if there is a loss here. If there's a loss, then energy is lost. So in other words, what this one would turn out to look like is it would come in at 10, and it might come in and have a loss so that instead of the 10, maybe it would have 9.5 here in the exit. So it turns out you would lose energy by coming through here. And it's possible too that this thing could go down here and lose energy here. And so there's a thing called hydraulic jump, which, see if I can find a description of it. Let's see, I misspelled it. Okay, maybe there's a good Wikipedia one. Hydraulic jump. Okay, so the first couple things you see is, okay, let me see if I can select this. You see the words accompanying violent turbulence. Violent turbulence, and eddies are created because of the loss. So if there's a loss, you could easily have hydraulic jump. And so he might actually give you some good pictures, and maybe he won't. Let's see how good that picture is. If you've here we go. This may be a good. So what happens is, here, I'll tell you what. It's probably not the best picture in the world, but so what happens is, let me add my problem to it. I'm going to match his color movement. So here's your water flowing in here like crazy. And here apparently is your ground. So what happens is it comes out from underneath the spillway, or whatever this object is. It can have a laminar flow region, which would be low or no losses. And then right before the jump, you might see something like this. But if you compare this to here, you'll find the velocity will slow here, so maybe it's going this fast here, and the exit may be going this fast. But if you compare Bernoulli's equation from this point here to this point here, you're going to have P1 plus gamma Z1 plus rho V1 squared over 2 minus some losses. There'll be an actual number here equal to P2 plus gamma Z2 plus rho V2 squared over 2. So in this little region right in here, you're getting eddies and swirling and all sorts of things that are losing energy or increasing this number, and which is that number with the minus sign in front of it. It's taking energy away from the initial state to the state down here, or in this case, it goes right about right here. So this is the very interesting to a person who's a civil engineer, but this, you've seen this. You've seen it in many different ways. Maybe he has some better. So here he's doing the same thing. You're applying continuity. For some reason I can't write on this page. And then you're doing something different. Oh, I know what. I'll select it now. You are conserving the momentum here. And we'll get to this soon enough. This is a couple sections later. And then, okay, you're down here, energy dissipated by hydraulic jump. That's a good example there. So what you see is the water flowing over fairly rapid, and then this white right here is the turbulence and creating a pretty strong hydraulic jump. And so you'll lose energy across the jump. Yeah, I think at this point we'll just call it quits, because we're not going to go in and calculate this. This is just the trivia of a later section. I don't think. Okay, so if you look at this, we're in here in Bernoulli's equation. We did fluid static. We're going to do a little bit of kinematics, but not a lot of that. And this is something that is, let's see, when you get to the very end of this, okay, I guess right here, this sets you up for this. And the control volume deals with, okay, so you got the conservation mass, which is essentially the continuity equation. Everything's going fine. Then, the Newton's second law in the momentum equations. And this is the part of that hydraulic jump I was talking about, although we're going to apply it in general and not specific to hydraulic jump. We'll go ahead and look at momentum, or linear momentum, and I'll do a little bit of moment of momentum, or essentially a torque. We'll lightly cover this chapter, and this is fairly important in fluids and heat transfer. And once we do it, this chapter is, the example is primarily focused on losses in a pipe. Okay, what happens is you go down to losses, and there are two types of losses here. The major doesn't mean the actually the value of the loss as far as the numerical value. It's just labeled that way for some reason. This is where you can find the loss in Bernoulli's equation, as well as this one too. These are two different types of losses that are just labeled in the way they are described. Now, we'll do a little bit of this, but if we get in here and you are interested in hydraulic jumps, because that's not the end of 10, I think it continues up here. Yeah, I guess so. Yeah. All right. They want the ring.